So, I think you'll notice that if you've been watching a lot of these videos, I'm now wearing something very, very normal, which means I'm doing all these videos myself. And I would really appreciate if you subscribe and you share on social media and things like that, because it takes a lot of time to make these videos and I just want everyone to benefit from them as much as possible, and I hope you like them. So, if we go here, we've got Born-Haber and related enthalpy cycles. So, giant ionic lattice, that's what it's all about. So, Born-Haber cycles are all about ionic lattices. Okay, so quick reminder on ionic lattices. All ions are attracted to each other in all other directions. And an example is sodium and chlorine, or sodium chloride. And you can see here we've got all of these ions surrounding that central one there, okay? And so it's very strong bonds because of that, because you've got ions attracted to each other in all different directions around the central ion. Now that means they have high melting points due to strong ionic bonds that take a high quantity of energy to break, or a high amount of energy to break. That is an exam answer, quite an easy one, so make sure it's in there, okay? Now, we're going to move quickly on to lattice enthalpies. Now, lattice enthalpy, this is a definition which you need to know for your exam. Okay, now what I really recommend is that when you're doing definitions, you can write down the equation for the definitions, because most of the time you won't have to remember these. You do have to remember this as part of your course, but the more likely question is, can you write out the equation itself? So, if we look at the different parts of the definition, if you know the equation, you'll know the definition because you can just write it from the equation. So let's show you what that means. So if we look here, formation of 1 mole of an ionic lattice. Well, there's 1 mole of an ionic lattice. Now all ionic lattices, because of high melting points, are solids. So that's how you know your S is there. Then it says from gaseous ions, okay, under standard conditions. Okay, so there's your gaseous ions. And you can see gaseous, gaseous, and you can see it's an ion that makes up the potassium chloride. Okay, so we've gone over our definition. So if we write this, we know it. So if I just don't look at that, and I can say, right, okay, what is it? Oh, it's ions, and they're gaseous. So I'm taking gaseous ions and making 1 mole of an ionic solid, or ionic lattice. Okay, let's move this up to the side. Okay, and then from here, let's have a look at why those changes are all exothermic, because they are all exothermic. It's an exothermic change, okay? And if that is the case, energy is given out when the ions bond to each other. So an exothermic change, energy is given out to the surroundings. Now, why is that? Well, it's all about this. So I want you to think carefully at this point. It indicates the strength of an ionic bond. So that value you're getting, that negative sign, that negative 711, there is indicating the strength of the ionic bond. Now, if it's exothermic, it's giving out energy to the surroundings. Okay, but why does that indicate the strength of the ionic bond? Well, think about it in the opposite way. Instead of forming this bond, which we are forming here, so we're forming this bond here, what if we go that way and we break the bond? If you break the bond, you have to put energy in. Okay, and that is called the bond dissociation enthalpy, or bond dissociation lattice enthalpy, because it's a lattice enthalpy in the other direction. So that means you're breaking them into gaseous ions. So I'm going from here to here. So as I go from here to here, I'm putting energy in. In fact, I'm putting plus 711. So plus 711. Now that means the stronger this bond is, the bigger this number is, the more energy I have to put in. And if you want to convert it to the lattice enthalpy, which is just the other direction, all you do is change the sign. So it's plus going this way, and it's negative going that way. Okay? And so the stronger the bond, the bigger this number for the dissociation enthalpy, breaking the ionic lattice apart. And because you're just changing the sign directly to get the lattice enthalpy, that means this will be more exothermic. So the stronger the ionic bond, the more exothermic the lattice enthalpy will be. So in order to calculate lattice enthalpy, we are going to have to go through lots of different definitions of different types of changes that you can do. And because lattice enthalpy cannot be calculated directly, it has to be done through the Born-Haber cycle. Now that makes sense after we've gone over the definitions, but let's go over the definitions first. Okay, so we picked a really simple one here for hydrogen plus oxygen goes to water. Okay, for your enthalpy change of formation. So enthalpy change of formation is when 1 mole of a product, there's your 1 mole of your product, is formed from its constituent elements. That's its elements, H2 and O2, okay, which makes your water. Okay, it's an exothermic reaction because of the negative, okay, which means in the other direction, if you were to break it up, it would be an endothermic reaction and would be positive. Now, that is the enthalpy change of formation, and to do Born-Haber cycles, you're going to have to get used to writing them for whatever is in the Born-Haber cycle. But again, that'll make sense when we talk about the Born-Haber cycle. Now, it's usually exothermic, but not always, okay? So most exothermic, but not always. Now, another example would be with an ionic lattice this time. So I did this just to make you familiar with your what you've done before, but now let's look at an ionic lattice, and we're starting to get used to putting these halves in as well, okay? 1 mole of an ionic lattice, okay? Notice the state symbols here. Can you see that? Now, if it was lattice enthalpy, that would be G and G, but this is S and G, okay? So S and G, because at standard conditions, 298 Kelvin, 25 degrees Celsius, that would be a solid. So the potassium would be a solid, and that would be a gas. And that's how you can tell this is not your lattice enthalpy. This is your enthalpy change of formation. Okay, you can see it's exothermic and negative. Now let's have a look at enthalpy change of atomization, okay, with that AT next to it. That's the enthalpy change when 1 mole of gaseous atoms forms from its element in its standard state, okay? So always endothermic because you're putting energy in, you're breaking bonds, okay? So you've got to break bonds. That might not make sense, so we tried to make this really, really obvious here. So we have got our atoms, okay, and let's imagine this is a metal, okay, so you might recognize this as a metallic bonding type diagram. You've got delocalized electrons. So this is a metal. We put energy in, okay, and then that breaks it up, okay, and we turn it into a gaseous. To break those bonds between them, we have had to put energy in to break those bonds, okay? So those bonds are broken, it's a gaseous metal. So remember the definition says gaseous atoms, so we are breaking bonds, so it's endothermic, you have to put energy in, okay, and you do that. And you'll generally have metals to do it because it's an ionic lattice that you're going to have to do with your Born-Haber cycles. So your Born-Haber cycles are all about lattice enthalpy, which means it'll be ionic, which means you'll have a metal and you'll have a non-metal. So your metal will normally be this process, and then your non-metal, for example, chlorine. Again, we're breaking a bond, but this time instead of breaking the metallic bond, we're breaking the covalent bond. Okay, so we've broken the covalent bond, energy's gone in. So you can see here our atomization. The important thing before we do the chlorine, because maybe you could stop the video now and try and do the chlorine yourself. Okay, look at the definition and then try and write it yourself. Things don't go in when you watch a video unless you try and do things during the video. So K solid going to K gas, really important, it's gaseous. Okay, really important at standard conditions, what is it? It's a solid. Okay, and it is endothermic, positive 89. Now really important, it says 1 mole of gaseous atoms. Now this starts off as Cl2. I want to create 1 mole of chlorine atoms. Okay, so when I'm doing it, I have to use a half. Okay, so, and they're going gaseous to gaseous because it was a gas originally, and it's still a gas. Okay, and we've broken that bond, but we're only using half. And again, endothermic. Again, and that is how you do enthalpy changes of atomization, and you could practice those in many ways. You could do it with oxygen if you wanted, you could do it with magnesium, you could do it with... You see, if you do it a few times, it becomes quite formulaic. Okay, there's only certain options that you can do with atomization, but the real important thing is, can you write these equations when you're given an element to do it with? So our next change is first ionization energy, and sometimes called IE1. Okay, definition from your first start of your A levels: energy required to remove 1 electron from each atom in 1 mole of gaseous atoms of an element to produce 1 mole of gaseous positively charged atoms. My God, that's a tongue twister. Okay, so that, but remember, in the second year of A levels, you're going to have to write the equation more than anything else. So the equation just is gaseous. So if we look up here, gaseous atoms, gaseous, 1 mole of it, 1 mole. gaseous ions, each losing one electron. Okay, so that is how you do it. So it's really important you can write these equations, and we'll go over that when we do the Born-Haber cycles as well. Now, really important you know it's an endothermic process. There's multiple choice questions which ask you whether something is endothermic or exothermic. Endothermic is when you put energy in. We have to put energy in to break the attraction between the outer electron and the positive nucleus. Okay, so we have to put the energy in. So it's always a positive endothermic process, energy in. Now, second ionization energy, i.e. 2. Energy required to remove one electron from each positive ion. So this time we're doing the same thing, but with a positive ion. Okay, in 1 mole of gaseous ions of an element to produce 1 mole of gaseous 2+. So we're changing it from 1+ to a 2+. Okay, so basically we're going from the plus ion to the +2 or the 2+ ion. Still removing only 1 electron, really important, and is an endothermic process. Notice this is not in green because it's not required for you to remember the definition, but it is required for you to write this. So you do still need to know how to write the equations. Now, you'll also be expected in the exam to explain why this is endothermic. And again, it's that attraction between the nucleus, the positive nucleus, and the outer electron. It's strong, okay? So you've got to break that attraction between the electron and the nucleus, okay? And it's even more difficult here because this is a positive ion, so it's got more protons than electrons. So it might be worth also saying it's got more protons than electrons. Okay, so next one, first electron affinity. Now, electron affinity is to love something, to want something, okay? So therefore, this is the gaining of electrons. So enthalpy change when 1 electron is gained by each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1-. So basically, we're going from an atom to a 1- ion. Now, again, it's really important that you can write the actual equations for this. So you start off with gaseous atoms. Now that must mean you must have atomized them already. So we're going to do this in order in a second, but you must have atomized them, broken the bonds between the oxygen molecules. Got your atoms here, and then you're going to add an electron on to make a minus ion. Now, why does that electron go in? That electron goes in because there are protons in here that are attracted to that electron. Because there's attraction between the incoming electron and the nucleus, so this electron and the nucleus, it's an exothermic process. It gives out energy. You can see here it's minus. Okay, so it's minus because the attraction between the incoming electron and the nucleus means energy is given out. It's a bond-making process, essentially. So think of it like that. So bond-making processes always give out energy. Bond-breaking always take in energy. So it's like that, if you think of it like that. So you have to explain it, which is why it's in green. So make sure when you're making your notes, that is in there. Okay, second electron affinity. Enthalpy change when 1 electron is added to a 1-. So basically it's a bit like ionization energy 2, but this time the second electron is going to be added. So it's going to go from a 1- to a 2-. So this is appropriate when it comes to oxygens, sulfurs, all that kind of thing, things that have 2- ions. So you go from here to here. Now, this is different in terms of the change. You're trying to add a minus to a minus, so a minus to a minus. A minus to a minus don't like each other. If they don't like each other, they're going to repel each other. So what you need to do, you need to put energy in. So positive amount of energy forced in, okay? So that is forced in, and that forces these two things together. So this is an endothermic process. It's endothermic because the electron is added. It's got to overcome the repulsion of the negative ion, okay? Because these two repel each other. Again, a exam answer for you. You will have to answer this. It's usually a 2-mark question in an exam. Okay, and that's our electron affinities and ionization energies. So we're going to move on to recognising and writing enthalpy changes. Okay, so this is when you're doing Born-Haber cycles. You're never going to have to draw a full Born-Haber cycle. This again won't make sense until I draw them, but you're never going to have to draw a full one. You'll have to do gaps, fill in gaps. And to do that, you have to recognise and write the enthalpy changes. Okay, so what I'd like you to do is stop the video and try and write out all of these changes. Okay, so I'm just going to give you a bit of a delay so you can get your finger to the pause button. Okay, ready? And hopefully you paused it, did all these, and then you come back. Okay, so first ionization energy of lithium. Ionization energy said both must be gas. You're losing 1 electron. 1 mole, 1 mole. Okay, enthalpy change of formation of calcium chloride. Calcium and chlorine are the elements that make up calcium chloride. At standard temperature and pressure, that's a gas, that's a solid. All metals are solid apart from mercury. Okay, and this is an ionic lattice, so therefore that's a solid as well. The lattice enthalpy of calcium chloride. Lattice enthalpy is the ions, gaseous ions, making 1 mole of an ionic lattice. Okay, so there's our gaseous ions. They're in the right proportions to make our ionic lattice. Enthalpy change of atomization of calcium. So if we look here, calcium in its normal state, a solid, and its bonds are broken, okay, making 1 mole of gaseous atoms. Really important, 1 mole. Okay, second electron affinity of sulfur, the minus plus an electron going to S2 minus. Okay, so really, really important that you can do all of those. Now, what's really good as well is if you could label all of those endo and exo. So ionization energy, you are breaking a bond between the electron and the nucleus essentially, so therefore that is endo. You not expected to know this one, it's exo. Okay, lattice enthalpy, that's exo. Okay, atomization, you're putting energy in, so it's endo. Okay, and this second electron affinity is also endo because you have to force the 2 negative parts together. So let's use all of this knowledge to do what we need to do, which is draw a Born-Haber cycle. Now, a Born-Haber cycle is just a fancy way of drawing a Hess's law, which you might have done in your first year. So we've got the energy on the left, and really important, if the arrow points down, it's exo, because the energy is going down. If the arrow goes up, it's endo, because the energy is going up. Now, let's have a look, shall we? For sodium chloride. So we're doing this for sodium chloride, okay? And it's really good to draw these. Even though in the exam you're never going to have to draw these, it's good practice to draw them. So if your teacher gets you to draw them, that's a good thing. It's not a bad thing. Okay, right, let's assume that energy is 0. And then we start. So we all start in the same way, so the same process. We start with our elements that make up our compound. So we've got sodium chloride. There's our elements that make our compound. And then we do atomization first. So atomization is always first. Write your notes down as I'm speaking. Atomization is first. And you usually atomize the metal first, then you atomize the non-metal. So I'm atomizing the metal. It's an endothermic change, therefore the arrow is going up. Plus 108, so the arrow is going up. The next one is going to be an endothermic change as well because it's atomization. Remember, I'm breaking the bonds, breaking the metallic bonds here, breaking the covalent bonds here. Okay, now remember, really important thing is get your balancing correct at this point. Okay, half of that is 1 chlorine. People often get mixed up with their balancing, get their balancing wrong. So we've got 2 endothermic changes. That's why it's really important that you know whether things are endo or exothermic. The next ones we do are ionization energies. So ionization energies, again, you're breaking the attraction between the outer electron and the nucleus, which means that it's endo again. So, but this time we only have to do ionization energy 1 because sodium doesn't go to 2+. And so normally we go to the top. So on this side is your atomization and your ionization energies. So this doesn't have to be to scale. So that's a really important point. It doesn't have to be to scale at all. Okay? Doesn't have to be. Okay? It can be any scale you want, but it must be in the right direction. So these are endothermic arrows. So they must be going up. Okay? So it doesn't matter the scale. Even though this is bigger than those two, you could have it that small. It still would be correct. It's fine. Okay? We're not doing it to scale. Right. Then we draw a line because what happens after that point is that we have to go to our next one, which is electron affinity. And we're going to go through about three or so examples of this so you can see it with different molecules. Okay? So electron affinity, because we've changed, and here we go, we've changed our sodium with ionization energy 2+, and we've kicked out that electron. So we've kicked out that electron. We've now got the chlorine. Okay, the chlorine needs to have an electron added to it for it to be electron affinity. So remember, the order is atomization, and then it is ionisation energy, and then it's going to be electron affinity. Now, electron affinity is an exothermic change, not an endothermic change. Therefore, the arrow is pointing down. Okay, so the arrow is pointing down. And the electron affinities are always on the right-hand side here because they go down. And imagine it like a circle like this. Okay, so from that, this is the case, we can then put in our electron affinity. I'll try and get my face out of the way here. Okay, and then you've got your electron affinity here, and the negative change arrow is pointing down. So we've got our gaseous ions. Now, hopefully now you can guess what the next one is, because the definition of lattice enthalpy is the bonding of gaseous ions to form 1 mole of a gaseous ionic lattice. Okay, not gaseous, sorry, an ionic lattice. Ignore the gaseous bit. An ionic lattice. Okay, an ionic lattice are always solid. So, if that's the case, again, that arrow goes down here, and we've got the solid. So this is our lattice enthalpy. Again, not to scale. I know I've done big arrows, but it doesn't matter. Okay, not to scale. So going down and then going down because they're both exothermic changes. Right, and then from that point, you've got to join the whole thing up with enthalpy change of formation. Hopefully you should see here that these are the elements, constituent elements. This is 1 mole of a product. Therefore, you draw an arrow between here and here. Now, if that's the case, this is exothermic, but they will tell you whether it's exo or endothermic in the question. We're just constructing one for now and showing you how you construct it. Now, how do you calculate different things? So what they'll do is they'll ask you to calculate a gap. So for example, it might be missing here. There might be a data point missing here. And they'll say, can you calculate the enthalpy change of the ionisation energy, the first ionisation energy? They'll ask you to calculate it. Okay, so we're going to go through a type of calculation of one of these values now and how you do it. And you do it by treating this like a Hess's cycle. Okay, so the Hess's cycle here, and you think of it like a circle like this. So I follow my arrows. Okay, and then I follow my arrows. And then blah, blah, blah. Oh, you notice that this one, this one, this one, and this one, and this one are all going in the same direction. So if you just do this, you'll notice they're going in the same direction. Okay, but one of them is not going in that direction, which is that one. Okay, so this one right here. That one is not going in the same direction as everything else. So we do this in terms of Hess's cycle. Okay, so really, really important. Let's move on. And you can see it here. So all these arrows are going in the same direction. And then this one is going in a different direction. Okay, that means we can add up all of the arrows in white. Okay, and it will equal the one in yellow. Okay, so let's put that down. Okay, and then you can add all the terms that go in the same direction. There you go. And there we go. So we're adding the atomisation. It's equaling the formation. We've got ionisation energy here. We've got electron affinity here. We've got lattice enthalpy here, which we're adding together. Okay, and we've got all of this like this. And that's your equation. Now, let's just say we wanted to work out the lattice enthalpy. The lattice enthalpy is over there, so all we have to do is minus everything in white away from the formation and bring it over. And that's what we've done here, just minus everything in white away from the formation. Okay, and then all we do is just plug the numbers in. That's simply all we do is plug the numbers in. If we plug the numbers in, we get the answer, which was already on there anyway, but we get the answer of minus 788. Okay, and that is how you do it. You find all the arrows that are going in the same direction, you add them all up, that will then equal the one that's going in the opposite direction, and then you rearrange the equation to get what you're asked for in the example. Now the only complications they can do is they can do electron affinity 2s and electron affinity, and ionisation energy 2s, and they can also just make it a bit more complicated by putting more than one element. So for example, MgCl2. So you've got 2 of those. So you'd have to times your atomisation by 2 and things like that. But we'll show you that in the next example. So this is the end of part 1. So we're going to move on to part 2, where we consider further applications and further different examples of Born-Haber cycles.